Problem 70. We have a pulley with a radius r and moment of inertia I. One end of the block, we have a block here M, is connected to an elastic spring with a constant K, and the other side is connected to a cord, and this cord is wrapped around the wheel, the pulley. The pulley axis and the incline are frictionless. We don't have friction between the axis and the pulley. The pulley is, listen here, initially we have the elastic object. Here we have the equilibrium position. We turn the pulley anti-clockwise to expand the system up with a distance x. Here we have the initial position at this point. Now I release the system without initial velocity, okay, at this point. Here at this point we have v equals to 0 and initial velocity of the pulley equal to 0. So we can say at time t initial we have omega initial of the pulley equals to 0 and v initial of the block equals to 0. Okay, find the angular speed omega of the pulley final of the pulley when the spring is again unstretched at the equilibrium position. When I release the system, the pulley, the block will slide down. I want to find the angular speed of the pulley when the block arrives again to this position. You know, at this position, the block has a velocity v. Here we have v, and here we have omega. So we can say at time t, the pulley has an angular velocity omega and the block has a velocity v, omega final and v final. I need to calculate omega of the system. Okay, I told you each time you want to calculate omega or v, you have to apply delta mechanical energy. In general, equals to omega f. Okay? Here I told you we don't have friction with the inclined plane. Mu equals to 0. So we have a conservation of mechanical energy. In this case, we can say mechanical energy initial equals to mechanical energy final. So the kinetic initial plus the potential initial equals to the kinetic final plus the potential final. Let's say initially we have the system at this position, okay, like this. This is the initial position, and the final position where the block is down at this point. Here we have initial, and here we have final. Okay, I take the lowest position as a reference. Here we have h equals to 0. And if you want, the distance between this point and this point equals to x. Here, here we have the height, as you see, the height between the initial position and the final position. And here we have x. So the distance here equals to x, here equals to h, and here equals to theta. Here, initially, the system at this point with initial position, we don't have velocity, we don't have omega, we don't have v, so we don't have kinetic energy. So the kinetic equals to O plus potential. At the initial position, we have the system. Let's start with the block M. The block M is at a height h from the reference h equal to 0. Okay, so the block M has a potential mgh. Now let's take the spring. Here we have elastic potential of the spring. So we have the elastic potential equals to half k x square. Okay. Here let's talk about h. To calculate h, we can take this triangle. As we say, here the distance from this point to this point equals to x. Here we have h, so we can calculate h by sine theta. We have sine theta equals to the opposite h divided by x. So h equals to x sine theta. So we can write directly here mg times x sine theta plus k over 2 times x square. Okay, equals kinetic energy final. At the final position, we have the pulley with an angular velocity omega. So we have the rotational kinetic energy rotational of the pulley, which is equal to I over 2 omega square. This one for the pulley plus at the final position, here we have the final position of the system. We have a velocity v. We have a translational kinetic energy m over 2 times v square. We have only this one. And at this position, the block has x equal to 0 at this position. And the block has 0 height. We don't have any potential energy, plus 0 potential. So we can write directly equals to I over 2 omega square plus mv square over 2. I need to calculate omega. Look here. The cord is attached to this point, the point A. If we rotate the disk, Here we have the velocity of the point A. You know, as the cord is attached to the point A, we can say VA equals to V of the block. And you know, VA equals to R times omega. So we can substitute the value of V equals to R times omega equals to R square omega square. Here we can calculate the value of omega. We have omega equals to m g x sine theta plus k over 2 x square. Okay, divided by I need omega. Here we have I over 2 plus m over 2 times r square. Okay, here I give you the numerical application. I give you the value of I, of R, of K, of M, D, and theta. You can calculate directly the value of omega, which is equal to 1.74 radian per second. This is the value of omega. If I ask you to calculate the velocity of the block here, you can say V equals to R times omega. We have omega, we have R, you can find V. The most important point here to get the relation between the velocity of the block and the angular velocity of the pulley.